Dr. Anastasia, you have 30 minutes and 5 minutes for the questions. All of them in a 30 minutes packs. Okay, please go ahead.
Hello, thank you so much for the opportunity to present my talk here. It's a very great conference, and I'm very happy to present my work. This work was done with my former student, Nikita Tsegelnik, and it's about, actually it's related to the studies of quark-gluon plasma, strongly coupled quark-gluon plasma, and we have considered two types of holographic backgrounds to study this. And first of all, let me remind just the basic of AdS5 conjecture, which states that classical strings on AdS5 background with certain relations between coupling constants and radius and fluxes are dual to N4 Superior-Mills theory. And I would like to stress that there are three types of the conjecture. So I mean three types of forms, and you can consider the strongest form, the strong form, and weaker form. And our studies are related mostly to the strong form. So holographic duality basically formulated for the zero temperature, but however it for sure can be generalized to the non-zero temperature. First it was done in the work of Wheaton in 98, and actually so you can say that considering AdS backgrounds with different types of asymptotics, I mean in different types of coordinates, you can formulate on its boundary conformal field theory. And so for instance, if you consider AdS space-time in Poincare coordinates, this space-time has typically flat boundary, and then you can consider it's dual to CFT on the flat space-time. However, you can also to consider AdS5 background written in globally coordinates, then you will have the so-called conformal boundary. I mean conformal Minkowski boundary, which has the topology R cross F3, and then your dual theory, so namely N4 Superior-Mills theory, can be considered on the space-time R times S3. So for certain purposes of which you study, you can formulate correctly the gravity prescription, and then you can consider some gravity observables to study the dual strongly coupled system. I would like to say that when you include temperature, then you for sure you lose conformal invariance and supersymmetries. And however, you can consider AdS5 black holes, which can be dual to thermal ensemble on N4 Superior-Mills theory at strong coupling. And then temperature of your CFT in the bath can be identified with the Hawking temperature of the black hole. And it's very interesting to consider AdS5 black holes with asymptotically with AdS AdS5 black holes with spherical symmetry for the horizon. Then you will have Hawking-Page phase transition, and it was shown at the same time. It was shown in the work of Sandberg in 2000s that 3 and 4 superangular theory on R times S3 at non-zero temperature will have a phase transition which happens at hydrogen temperature. And it was considered further in the works of Harmack and his group. And that's why it somehow motivates us to study more carefully AdS5 black holes with spherical symmetry, with spherical symmetrical horizons for the quark-gluon plasma. Why quark-gluon plasma? Quark-gluon plasma, it's a strongly coupled system. At high temperatures, it has so-called quasi-conformal behavior. It means that the trace of the stress energy tensor tends to be at 0. Here I show on the left-hand side, I show the picture, the behavior of the trace of the stress energy tensor. So first it has around 200 MeV, it has some conformal anomaly, and then it tends to be 0 at high temperature. So around more than 300 MeV, it tends to be 0. And it was this picture is from the lattice simulations. So it's somehow it motivates us to apply AdS50 correspondence to study quark-gluon plasma at least at the stage of equilibrium stage. And I would like to recall some very important example of the studies. It's the shear calculations of shear viscosity for QGP. For sure, it was done for black brain for the black brain at with the flat horizon, but it was checked on the rig and LHC. And I also would like to say that rotating quark-gluon plasma, it appears in the calculations of I'm sorry, it appears in the nuclear, in the heavy ion collisions, and typically it's not non-central heavy ion collisions when each of the beam has its own angular momentum, and then the whole system after the collision rotates with some amount of the original angular momentum. So here I present on this slide, I present the holographic model. So it's very simple. It's 5-dimensional action with the scalar curvature and the negative cosmological constant. The black hole solution which this theory has, it's the anti-de Sitter Schwarzschild black hole, and here down here for now it's the blackening function. So it has 3 terms. L it's the size of the AdS black hole background. M it's the mass parameter, and also this theory has the Kerr AdS solution. So here I also represent. I'm sorry, it's my slide. Yeah, so on this slide you may see this metric for this Kerr anti-de Sitter solution. It includes also besides the mass, it also has 2 rotational parameter, which are related to that it's higher dimensional black hole, and it's these parameters A and B, and so there is also parameter delta, which depends on these parameters A and B, and this theory both AdS Schwarzschild and Kerr AdS black holes. They have conformal boundary which can be called Einstein universe. So it's it's compactification on Minkowski spacetime, and here are down this boundary. And yeah, I would like to stress that here I presented the metric for the Kerr anti-de Sitter solution in the case when it's so-called non-rotating at infinity frame. So the black hole rotates, however, but on the infinity the system doesn't rotate. Well, here it's the calculation of the free energy for the black hole, and as I said, these black holes, both Schwarzschild and Kerr AdS, they have a Hawking-Page phase transition. So Kerr AdS5 black hole inherits this Hawking-Page phase transition, and there is what we can see. We have the from this picture we see that these parameters. The rotational parameters affect on the free energy, on the behavior of free energy. So, and we have some maximum values of A and B, so the rotational parameters, when the Hawking-Page phase transition just disappears. And here I present the behavior of the temperature with the dependence on the behavior of the critical temperature with the dependence on non-zero rotational parameter, and I show that we have the greater value of the critical temperature can be reached at when the black hole doesn't rotate. So it means that it corresponds to Schwarzschild-AdS5 black hole. And if we will include rotation, so switch rotation, then we will obtain that the critical temperature will be smaller and smaller. And yeah, so we can find the dependence of the temperature on the both rotational parameters here I presented. And what I would like to say is this behavior actually was already found in the literature, was already known. There is a paper by Chen and others where it was studied for the other black hole system. But it's rotating black hole, but with just one rotating parameter, and it was shown that the temperature of the phase transition just decreases with the increase in rotating parameters. And what we have for the lattice models and for the other calculations, for instance, for the effective models, the effective models of rotating QGP say the same. It was shown in the works of Webinar, Chernobyl and Gonio. However, in the lattice calculations, so in the works of Braguta, Kotov and others, which are actually from my institute, they have shown that the phase transition temperature can increase, and this can be found in a totally gluon system. So if you have gluon, just gluons, and for the lattice simulations, and use SU2 group, then your temperature will begin increases. Actually, it's some puzzling behavior, and they found also that including quarks can change. So what kind of observables I'm going to consider in order to test my strongly coupled QGP, which is defined in RS3 background. I'm going to show how I'm going to show the behavior of the quark-antiquark potential and jet quenching parameter. Well, as you I already formulated that AdS safety conjecture states that classical strings in AdS background dual to some observables in 4 superangular theory. So an open string with 2 endpoints on the boundary, considering an open string with two endpoints on the boundary, you can calculate the for instance, rectangular Wilson loop, spatial or temporal, and you also can calculate the light-like Wilson loop, and from the light-like Wilson loop you can find out the jet accretion parameter. So it's the parameter that estimates the energy losses of heavy quark and quark-gluon plasma. And well, here we use the ordinary holographic prescription for the calculation of Wilson loop. Here I wrote down the definition of the Wilson loop for the N4 superangular theory. And as you know, in the work of Moldacin, it was stated that the Wilson loop is due to the number go-to action of the string. So, and the number go-to action can be calculated as usual. So you should consider the induced metric of the string Schwarzschild, and this should be minimized, and also it should be regulated or renormalized, since the AdS black hole, as ordinary AdS, have infinite volume, and then all your observables will be divergent on the boundary. And well, first calculations of black hole, first calculations of holographic Wilson loops in the black holes, it was actually AdS backbrains. It was done in this work, so Anastasia and Tyson. And also it was why it's interesting for people who are working in QCD, because using calculations of Wilson loop in holographic strongly coupling in a holographic background, you can predict the quark-antiquark potential for the quark-antiquark pair in the strongly coupled quark-gluon plasma. And here I've done the relation. If you have some contour C, then the expectation value of the Wilson loop will be defined as exponentiate of the quark-antiquark potential. And this works when the temporal direction, so the time, tends to infinity. So if you will take the prescription, holographic prescription, that number go-to action is defined through the number that the Wilson loop is defined through the number go-to action, then you can find out that you can find the holographic potential just calculating the string number go-to action, which is minimized. So here I wrote down again, then first I would like to start from the Schwarzschild-AdS black hole. Here, so it's the black hole with the spherical horizon. Here it's the blackening function. It has 0 at the location of horizon. The temperature is defined as usual through the surface gravity, and the number go-to action with the you can calculate immediately with of the number go-to action for this for an open string, which both endpoints located on the boundary of this black hole, and so it's stretched to the horizon. And here I wrote down the parameterization, the boundary condition of the endpoints. Here I presented the picture for this string, which is located. So this is the boundary, this is the location of the horizon, and so the string is stretched here. And here it's the calculation of the number go-to action. You use ordinary holographic prescription, calculate the integral of motion for this, and find the turning point. Using the equation of motion for the turning point, you minimize the action. You see that you find also the distance between quarks. Then you see that taking to the limit r to infinity, where the boundary is located, you find that the number go-to action is divergent. You need to do renormalization. And then you do the subtraction of the self-energy of heavy quarks. And here I presented the pictures for the behavior of the quark-antiquark distance. Here it's You see that it's the dependence of the quark-antiquark distance on the constant of integration, which is related to the conserved quantity, the Hamiltonian. And here I wrote down the distance between the quark-antiquark pair as a function of this quantity. And also I presented the quark-antiquark potential for various temperatures and various angles. So you see that you can change the angle, and then and you also can changing the temperature. So increasing the temperature, you have the smaller distance between quark-antiquark pair, and so it means that you go deeper and deeper into the UV. So what is interesting here, we can also find the exact relation between the quark-antiquark pair, quark-antiquark potential, and the distance, quark-antiquark distance. And here we do some trick. We consider the renormalization, the renormalized action, and it's some. So as you have seen, it's some integral, and the distance between quarks is also some integral. And then you will find that it have some relation if you will find the derivative with respect to the constant c. The parameter c, and then it leads to this relation for the renormalized action, and finally you will find this relation for the quark-antiquark potential. It's this is very nice since you have the derived L here, so it's separated from the part which is described by this integral. And actually you can try to what we have done in our work with Nikita. We show that this integral behaves as the Coulomb part. Here it's Wilson loop in the Kerr anti-de Sitter black hole, and here I wrote down Kerr AdS black hole written in the non-rotating at infinity frame. And again you have this parameterization for the string pole sheet. I will skip all this machinery for the calculation. It's generally the same for the Schwarzschild-AdS. It differs just by quite judicious calculations related that the metric coefficients for this black hole is quite unpleasant, I would say, and that you just need to introduce some redefinition of the metric coefficient. This will help you to calculate the renormalized number Gaussian action and the distance between quarks, but generally it's quite the same. Here I presented the behavior of quark-antiquark potential and the distance between two antiquark between the quark-antiquark pair with respect to this quantity. And you see that increasing temperature, again your potential is deeper and deeper in the UV, so you have the smaller value of the smaller value of the distance. And I would, again you can use this trick to find the relation between the number quotation and the quark-antiquark distance. You can just derive the linear part that can be associated with the confinement, and the Coulomb part which is related to the confined phase. The second quantity which I would like to show the calculation is the jet quenching parameter, and well, it's this parameter estimates the energy losses. It's related with the energy losses of heavy quark and the strongly coupled system. The prescription comes from the work of Leo, Gopal, and Weidman. It said that you need to calculate light-like Wilson loop, and this calculation can be done actually with using ordinary quantum methods, and then for sure it's some order to next to leading order prescription, but however you can then apply this to holographic calculation. So and this, from one side you have this expectation value of the light-like Wilson loop that is related to head Q, which is quark. It's the jet quenching parameter, and it determines the square transverse momentum of quark, which propagates in the quark-gluon plasma. L minus it's the extension of the light-like direction, and L is an extension in the transversal direction. And remembering that the Wilson loop can be calculated in the holographic, under holographic approach, through the number Gotti action, you can immediately find that the jet quenching parameter can be calculated through the holographic Wilson loop. Well, I will briefly describe what we have done. It's we introduced the light cone coordinates in order to find the light-like Wilson loops. For Schwarzschild-AdS5 background it's quite easy, but for Kerr AdS it's actually non-trivial. We used the prescription of Marek-Taylor work. Here again you need to calculate the number go to action to minimize it, and instead of using some arbitrary C, which is related to the turning point and the conserved quantity, you need here to expand this in series, and so you do for calculation for small c. In this way you will find the jet quenching parameter. Here I presented the jet quenching parameter for the non-rotating background, and for high temperatures we have shown that it behaves as squared temperature, and here I presented the dependence on them for different angular parameter theta, which is related to the geometry of the background. And you see, this dashed behavior is for and for super Mills calculations, so for AdS5 brain with the flat horizon. And you see that it can be, for the Schwarzschild-AdS5, it can be very close to the N4 superior case. However, you can turn this parameter and you will obtain smaller and bigger behavior for this. And then here it's, we have shown this behavior Q hat over T in the third, and we have shown that at high temperatures it tends to conformal behavior. And the same calculation have been done for Kerr AdS black hole for the rotating system. And yes, here a bit tricky because of the rotating background, and unfortunately we are not sure for our parameterization or light-like coordinates. But however, we have quite nice results for the behavior of the jet quenching parameter. It can be generally it's greater than the case of the Schwarzschild-AdS5 for non-zero rotational parameters, which are both non-zero, so both rotational parameters non-zero. And however, when you study high temperature behavior, again we have this behavior behavior like temperature in the third power with some coefficient which depends on the rotational parameters A and B. So let me conclude. So we have calculated the temporal and Wilson loops and also light-like Wilson loop. From temporal Wilson loops, we have found quark-antiquark potential. For both backgrounds, we have seen that it also includes Coulomb-like terms, and for the temperature, which about the critical one, we have the Coulomb-like behavior. This quark-antiquark potential can be, it depends on the angle and on the temperature, and increasing temperature or reducing angle, you can find that the distance decreases between quarks, and also the same happens for the non-zero rotating parameters. And also we have seen that the quark-antiquark potential can have the same quark-antiquark distance. So I mean that for the same quark-antiquark distance, you will have the same value of the potentials, and that's why at high temperatures in both backgrounds we have seen that the quark-antiquark potential tends to be equal to the case of flat horizon, to the case of AdS backbrain. I mean,
Thank you very much.
for the jet equation, we have seen the strong dependence from the angular parameter theta, and we have seen that for high temperatures we have the cubic dependence. And this happens both for the Schwarzschild and Kerr AdS black hole, and yeah. So I think that that's all that I have that I would like to show you. So thank you very much for your attention.
Thank you very much for your nice talk. And any question?
Oh, I've seen that some questions in the chart. Because of rotation of QGP, we expect radiation of charged particles. How do you consider the energy loss of rotating objects by radiation in your study? Well, unfortunately, it's not done in our work. I know that actually the person, Kazem Fadafan, I know these works that where it was considered rotating particles in the quark-gluon plasma, non-rotating quark-gluon plasma, and energy losses of this. For these backgrounds, I would say that it's a bit tricky, and we have tried to do this a couple of years ago, but then we unfortunately we have to stop these calculations. Yeah, probably we will come back to this soon, but before it was we were restricted in actually with our technique. Now we have what I would like to say, that the black holes with spherical horizons are not pleasant. So this dependence on angles and this relation for the horizons, it's not really good for the calculation for the numerics, and we have improved our, so recently we have improved our calculation Mathematica, so maybe I hope using your prescription for the rotating charged particles we would do something.
And I guess we had a problem for the internet interruption, and Dr. Kim wanted to finalize his talk, but if you let me, Dr. Kim, we can postpone your 3 minutes to the last talk of this session. Thank you. So our next speaker is Dr. Xiaowan Bai from School of Physics, Sun Yat-sen University of China, and he will give us a talk about holographic entanglement spectrum from hyperbolic black holes with scalar hair. And Dr. Bai, you have